Putting things in order. I mean, it sounds so simple, right? You put your socks on before your shoes. You lay the foundation before you build the walls. But what happens when you have hundreds of tasks and dozens of them all depend on each other? All of a sudden, that simple to-do list becomes this tangled web. Today, we're going to unravel that web using a really powerful idea from computer science. At its heart, this is a problem we all face. Whether you're building a house, compiling code, or literally just getting ready for your day, the sequence of events is absolutely critical. It's just a fact of life. Some things simply have to come first. So let's break it down with something super simple. You're getting dressed. You've got socks, you've got shoes. In what order do you put them on? Now, I know it seems obvious, but the logic behind your answer is the absolute key to everything we're talking about today. Of course, socks first, then shoes. It's the only way that makes sense, right? This isn't just a preference. It's a fundamental, unbreakable rule in the process of putting on footwear. I mean, just think about what happens if you try it the other way around. You can't put your socks on over your shoes. It's just not possible, it makes no sense, and let's be honest, it would look completely ridiculous. This really drives home the point that some rules of order are totally non-negotiable.
And, in the world of computer science and project management, this simple rule has a name. It's called a dependency. Putting on your shoes is dependent on first putting on your socks. The real challenge comes when you have hundreds of these dependencies all tangled together. You need a way to manage them.
So how in the world do we map out a whole network of these dependencies? We can't just keep it all in our heads. It would be impossible. What we need is a blueprint, a visual map, and that's where graphing comes in. And here is that map. This is called a directed acyclic graph, or a DAG for short. It's pretty simple, actually. Each circle is a task, and the arrows, well, they show the dependencies. So for instance, that arrow pointing from B tells us that B must be finished before we can even think about starting A or D. Now, the cool thing is the name itself tells you the two most important rules. It's directed, because the arrows are one-way streets. The dependency only goes in one direction, and it's acyclic, which is just a fancy way of saying there are no loops. You can't have a situation where task A depends on B and task B circles back and depends on A. That would be an impossible, endless loop. Okay, so we've got our map. Now what? The big question is, how do we find a valid path through it all? How do we turn this tangled web of dependencies into a simple, straight-line to-do list? Well, that process has a name. It's called a topological sort. Now here's the formal definition. It's a linear ordering, such that for every directed edge from vertex U to vertex V, U comes before V. Let's translate that. All it means is creating a flat list of our tasks that respects every single arrow in our graph. If there's an arrow from B to A, then B has to show up earlier in our list than A. Period. No exceptions. And this makes it crystal clear. Let's look at our little graph again. In order like B, then A, then D, then C. That's totally valid. Why? Because B comes before A and D, and A comes before C. It respects all the arrows. But in order like A, B, C, D, no way. That's invalid. It breaks the very first rule by trying to do task A before task B when the graph clearly says you can't. Okay, this is easy enough for us to figure out by just looking at 4 tasks. But what if you have 400 or 4,000? How does a computer navigate that massive, complex web and find a valid path? Well, for that, you need a system. You need an algorithm. And one of the most popular ways to do this is called Kahn's algorithm. It's a really elegant step-by-step approach to solving this exact problem. So let's walk through it together. All right, here's a bigger project. Again, the arrows are the dependencies, but notice those little numbers next to each task? That's called the in degree. It's just a simple count of how many arrows are pointing to that task. So you see task D has a 3 next to it. That means it has 3 prerequisites that have to be finished before you can even touch it. The logic of Kahn's algorithm starts with a really simple, powerful question. Where can we possibly begin? And the only logical answer is to start with the tasks that have no prerequisites, right? The ones with no arrows pointing to them. In other words, the tasks with an in degree of 0. So if we look at our graph, we can immediately spot 2 tasks that fit the bill, task B and task G. See? No arrows pointing at them. They aren't waiting on anything else, which means they are our starting points. we can go ahead and add them to our sorted list right now. So B and G go on to our final list. Now, here's the crucial move. We pretend they're done. We mentally complete them by removing them and all of their outgoing arrows from the graph. This one move is what unlocks the whole rest of the puzzle. And watch what happens the second we do that. With the dependencies from B and G erased, tasks A and F are suddenly freed up. They were waiting, but now their prerequisites are met. Their in degrees drop to 0, which means they're next in line. And that right there is the beautiful simplicity of the whole thing. We just keep doing that, over and over. Find all the tasks with no prerequisites left, add them to our list, and then remove them from the graph. We just keep rinsing and repeating until there are no tasks left. And by following that simple, repeatable process, the algorithm chews through the entire graph and spits out a valid linear order. In this case, one possible correct answer is B, then G, then A, then F, D, C, and finally E. Every single dependency is satisfied. Problem solved.
So, we've untangled the web. We've seen how to map out all our tasks and how an algorithm can find a valid path through them. Let's just quickly wrap up with the key things you really need to remember about this whole process.
First, and this is huge, this only works on DAGs, those graphs with the one-way arrows, and crucially, no impossible loops. Second, the final order isn't always the same. In our example, we could have done G, then B at the start, and that would also be correct. There can be multiple valid solutions. And third, this thing is fast. It has what we call linear time complexity. All that means is if your project doubles in size, the time it takes to sort it just doubles. It doesn't explode exponentially, which makes it perfect for gigantic projects. If you remember just one thing from all of this, let it be this golden rule. This is the entire point. For every arrow in that graph, the task at the start of the arrow has to come before the task at the end. That is the non-negotiable principle that makes it all work. And that leaves us with one final, very important thought. This entire process, this whole beautiful algorithm, it only works because our graph has no loops. But what happens in the real world when a project gets stuck in a circular dependency? You know, where task A needs B to finish, but task B needs A to finish. What happens then? How does an algorithm handle a situation that's literally impossible?